Hi guys, today we'll be learning about work done for reversible isothermal process in thermodynamics. So let's start with the basic piston cylinder assembly. Here initially the piston is at position I and from here it is compressed to a position F by a block of mass M. The external pressure Pext is applied by this block and it sinks the piston down to a depth h. The gas is filled inside the cylinder, at pressure Pint, and the cross-sectional area of the cylinder is A. Okay. Now we move on to find the work done for the piston cylinder assembly. The work done in any general case is given by force, that is F, into displacement S. Here this displacement is specifically in the direction of the force. So for this piston cylinder assembly, the force is nothing but the weight of the block. So we can say that force is mg, and the displacement in the direction of this force is the depth h to which the piston sinks down. Now if I divide this thing by a and I multiply this by a, then mathematically there is no change, but if we look at it from a different perspective, then this former thing, it is nothing but the force upon area, which is the pressure. So it gives the pressure Pext, which is exerted by this block of mass m over this piston. The second quantity, it is h into a, area of cross section. This is nothing but the volume which is displaced by the piston as it sinks down from position I to position F. So we can say that the work done is given by Pext into V displaced into the volume displaced. Okay. Therefore, the work done by the piston is integral of minus Pxt into dV, where dV is the change in volume. Now, to justify this negative sign, we would go back to the piston cylinder assembly. Here we are considering the compression case, so the final volume will be this much, Vf, and the initial volume was this whole thing, Vi. It is quite clear from the diagram that V final is less than V initial. So this means that dV, which is the change in volume and which is given by V final minus V initial, it would be a negative quantity. So in this formula, dV is negative, and when we multiply a negative thing with a negative sign, it means that this whole thing would in total be positive. So we can say that the work done in thermodynamics for the case of compression is always positive, okay, like we have seen over here. And work done in the thermodynamics for the case of expansion is negative. Now how does this happen? We'll go back to the piston cylinder assembly. Here again, if the case was of expansion, then initially the piston must be over here. This should be initial position, and finally it should reach over here. So this would mean that this would be the initial volume of the piston, and this whole thing would be the final volume of the piston. So in that case, V final would be greater than V initial, and the change in volume dV would be a positive quantity. So in this formula, dV would be positive, and if we multiply the positive thing with a negative sign, then the whole thing in total would become negative. So the work done by a piston for expansion would be negative, and that's what we wanted. So this formula is justified for both the cases, for expansion as well as compression. Now we move on to the reversible isothermal process. Here a similar piston cylinder assembly is kept, but the mass is added. The mass that we add over here are in the form of infinitely small grains, okay, and the mass of each particle is dm, such that dm tends to 0. It's infinitely small mass. You can assume that dm is similar to a grain of salt, that small. That way, each time you add a single grain of salt over the piston, the pressure of the gas increases by an amount dP, and dP would also tends to 0. Also, the piston sinks down by a distance dh. Let's say that the piston has sunk down by this much amount. I'm exaggerating the view for better understanding. but this distance to which the piston sinks down is very small. Let's call this distance dh. So dh would be very small. Now when the piston is sinking down and when it has come to the new equilibrium position at dh depth, the pressure of the gas inside the cylinder and the pressure due to all the grains above the piston would be equal. Okay, the pressure inside the cylinder and the pressure due to the external pressure would be equal, and we'll call this pressure P. Also, the equilibrium is established instantaneously. This means that each time we add a grain of salt over the piston, the change in pressure dP is very less, so the piston moves down and quickly regains the equilibrium. The third point is each step is reversible. This means that if we start removing the sand from the piston particle by particle, then the piston will start moving upwards. So that way we can say that that's why the process is reversible, because it can go in the reverse direction. So now as we add the particle grain by grain, each time we add a new grain, the piston shifts down by dh distance till it would reach the final point F. Okay, and this final point of completion would occur after infinite steps, and it would take infinite time, because size of the grain is infinitely small, and therefore when the final point is reached, when the piston has reached the point F, then there would be a pile of heap of sand over the piston, and the mass of this heap would be complete m. So we can say that the work done in this process is minus integral V1 V initial to V final, and P external, as I have shown you here, that P external is equals to P, so P external into the change in volume dV. Now we move on to the ideal gas equation. Here ideal gas equation is PV equals to nRT, where P is the pressure, V is the volume, N is the number of moles of gas trapped inside the cylinder and its constant, R is the universal gas constant, T is the temperature. Since we are talking about the isothermal process, so temperature will also be constant. So on a whole, this whole thing on the right side is nothing but a constant, and I'll denote it by C. So we can say that the product of pressure and volume is a constant quantity for a particular piston cylinder assembly, and if we talk about the pressure and volume at two different states, like at state 1 the product will be P1 V1, and at state 2 the product would be P2 V2. So the pressure volume product at these two states will be same. So we can say the work done is given by, from here it is given by minus integral V initial to V final P dot dV. From this ideal gas equation, I am removing P from the left side and I am putting it in the denominator of the right side. So we can write P is equals to nRT by V. In the work done, I can replace the value of P by nRT by V. So this becomes integral V initial to V final nRT by V into dV. As I have told you earlier, this nRT thing is a constant, so we can take it out of the integral. So this becomes minus nRT integral V initial to V final dV upon V. This can be written as minus nRT. The integral of dV upon V is natural log or ln V. This can be written as ln V. Limits from V initial to V final. Now this is equals to minus nRT ln V final minus ln V initial. So the work done becomes minus nRT ln V final upon V initial. Thank you for watching.